Well, I hope that we're working now. For some reason it's gone a little bit with this picture, but I've combined the last couple of lectures into one. So this is the last lecture you'll get for the unit. I've got a little goodbye message for you at the end. But it doesn't mean the tutorials stop. They will continue so that they can support the assignment. Number 3, I'm still working through assignment number 2's marking at the moment. Generally looking better than assignment 1, which is what we want to see. So let's have a look at these various things. So I've rolled in plastic and glass and a few other bits and pieces together. So as always, we say up here, read the essential stuff and more. So the essential readings, and don't forget to look in the files tab to find the supporting readings and everything that I've been emailing out to everyone through Teams. Just scroll back through those to find the other stuff that's out there. If you hear any coughing or anything in the background, it's my dog. Unfortunately, he's 14 years old and he's got heart failure coming on, so he does cough every now and then to bring up liquid from his lungs. So it's not me, I haven't got the virus. Alright, so let's have a go and let's have a little look at plastics. That's not what I wanted to do. Why have I got that? Plastics. Now there's 8 different types of plastic. I don't really want to read these word for word. I will be putting up the PDF of the lecture along with the recording, so you'll be able to print them out and have a look at them all. Just give you some background that this really builds upon or gives you the underlying knowledge you need to know for materials 2 that you'll be doing later on. Polyethylene is a very old plastic, one of the earlier ones that was discovered. It's a monomer, it's only got one polymer, so it's not particularly strong. The important bits to notice up here, it's got different densities to other ones. It's got low crystallinity and low density, low pressure polyurethane. So it's not a strong, it's not going to be used for any structural purposes. Okay. It's got some hardness, it softens very easily under temperature, but as you soften it and as the temperature goes up, the strength does increase. However, as it gets a bit warmer, its impact toughness drops and its elongation will decrease, it'll snap. You tend to find that this particular plastic, although it's flexible in low temperatures and things like that, is, well, it has been used for pipes and things like that, but it's more in plastic sheets than that nowadays. If you were to have a look down here, and as I always say, I'll open these up as we go to make sure everybody sees them. This is a specialist plastics website. Okay, so I'd like you just to have a skim through this. This really goes in with the sustainability question later on. It tells you what the impacts and the issues and alternatives to plastic are. As with the rest of society, we have become addicted to the use of plastic. It got its way into construction quite early on, really, in the adoption of plastics. But we've now got massive problems with its lack of recycling sometimes. It doesn't tend to decay. So read through all of this. This is all quite interesting information to show you why maybe we shouldn't be using plastics if there's a greener alternative. Okay, so we've got all these things, there's different plastics, life cycle analysis shows plastic is better. That's because it lasts so long. Now, that doesn't mean it's particularly good. So I'm going to allow you to go and have a look through this all on your own, at your own speed. I may try and print it out as a PDF for you. So polyvinyl chloride plastic, that's quite a popular one, very common in construction. Okay, tells you how to do it. It doesn't age very quickly, but it doesn't like heat. So it's no good putting it somewhere that's going to get hot. It can decompose, at over 100 degrees centigrade. It likes to be below 60 to 80 degrees centigrade. You'll find this is used in a lot of, what we use it? This again, pipes, and it used to be used for electrical insulation. Polystyrene plastic. Okay. It's quite transparent, so you can sort of use it in place of glass if you want to. And you can change the colour of it if you want to get disco type effects. It's pretty good with most chemicals. It's water resistant. You can put pigments in so it's light resistant. It stands up to UV fairly well. However, it does, and it's cheap. However, look at the red bit down here. It's got some fairly, from construction point of view, bad drawbacks or disadvantages. It hasn't got a lot of stiffness. It's a bit flexible and bendy. If you bump into it, it'll crack and split. Not good if it gets hot. And if it gets too hot, it will catch fire and it will then start pumping out the poisonous and deadly fumes that come from the place. So there are big restrictions on what you can use this for. Polypropylene. This one's quite better. This is really good. It doesn't go soft. It doesn't catch fire terribly easily. It does have weak points again. It's not stiff if it gets cold, so it can shatter, snap and split in very cold temperatures. And it's not very good at keeping the air out. It's you wouldn't use it to create a airtight room or something like that. So it's best used indoors. So you might find out things like some light switches or stuff like that could be made of it. There's no set plastic for a set use. There's various choices for them. Thermoplastic resin, some reason called organic glass. It's got very good light transmittance, very transparent. It's got high strength at a low temperature, which is really good compared to the last one. Doesn't absorb water. Got a bit of heat resistance. It's not really an insulator on its own, it can be, but it scratches easily and it's expensive. So they'll have to be careful where you used it so it wasn't exposed to wear and tear and rubbing. And polyester resin, it's good, it's quite strong, it's elastic, you can colour it, it's flexible, it puts up with heat and it resists water. And you can actually use this almost like a thread, and you can spin it and weave it. And phenolic resin. This is one I never really come across too much. It's good for corrosion resistance. It's good at high temperatures. It doesn't fall apart with UV radiation. There's not a lot to say about this one because I couldn't find any particular materials that were made of this yet. But I'm still looking, and if anyone out there finds something in the construction industry made from this particular plastic, let me know. I'm still trying to find out myself. Never come across it in my professional life. Silicon resin, yeah, I've seen this one a little bit. It's basically what, as you see, it goes straight to the bottom. If you play about with it a bit, like we make alloys out of metal, well, you can actually make glass fibre out of this, and you can weave asbestos in the glass fibre to make it fireproof, but it's got to be the correct asbestos, not the bad stuff. So obviously glass fibre goes into glass reinforced plastic. Glass fibre can be spun into thermal insulation blankets. So it's got quite a lot of use, that one has. Often don't think of it as being a plastic. Some examples of plastic materials here. So we've got cladding panels. So here's some cladding panels. There isn't a picture of everything. Cladding panels here, you can look at buildings as you're walking around and you might go, it doesn't look like wood, it's probably a cement board, like a hardy board, but it could be this. Personally, I would never bother using them. They do age and become a bit brittle, and they can discolour over many years because of the ultraviolet radiation from the sun. But they're fairly cheap, and well, they're cheap because of the labour costs are low in whacking them up onto a building refurbishment. Personally, I wouldn't use those in a new build, but you know. Then there's cables. We talk about cables. Well, it's the insulation on the cables down here. So big cables, little cables, they've all got a plastic insulation on them. And you get pipes and gutters, like rainwater down pipes and gutters. You see those all around the place, so no point showing you a picture of those. Windows and doors, plastic windows and doors, UPVC is quite a common one for that. Ultra polyvinyl, can't remember the full name, I'm terribly sorry, I'm useless. But as you can see, here's a section through a window made of it, and it's very complex. And that's all there to give it strength, and the air voids also managed to entrap some air as a thermal insulation to stop a cold bridge. Imagine if this is the outside, and this is minus 20 degrees, and in here it's 24 degrees plus. If that was solid, then this minus would be minus on the inside, and you get condensation. So all this is insulation to stop transfer of heat through the tube, and that's a triple glazed window as well. These would be filled with an inert gas, not air, by the way. Shuttering, rather like formwork, really. If you're pouring concrete or something, you can put it in, and it can be left in place. Wall linings, you can line, normally in more commercial uses, commercial industrial uses, not residential. And you can find in offices, demountable partitions may well be plastic surfaced linings, and if you go into things like deep freezes and cold stores, they could well have linings the same. Floor coverings, well, you just have to look at things like thermoplastic tiles or sheet flooring like lino or whatever you want to call it nowadays. That's all plastic based. Ceiling panels, quite often you can find plastic ceiling panels. Roof coverings, well, yep, roof coverings. There's a man doing a roof covering up here, and it's sheet waterproof plastic which rolled out, it's bonded to the roof surface. That probably insulation was meant to stand on there, and you might have 2 or 3 layers bonded down, but you can use that, and you can get rigid plastic sheets that look like tiles if you want to pin those on as well. Again, not something I would use. I tend to stay away from the plastics as much as I can. When we were talking about ceiling panel, roof coverings, sinks, baths, basins, well, you know, quite often you'll find that your toilet, your hand basin and all that stuff is plastic. Here is a unit that comes as one, so there's your bath and your shower. That's all plastic. I prefer ceramic, but it's plastic. Worktops, yep. Quite often the worktops you find are plastic. They could be solid plastic, or they may just be plastic coated. Insulation materials, well, again, insulation over the, electrical insulation on the cables, or thermal insulation fitted to walls. So that's an expanded foam, a rigid foam that's been put onto the walls, but it's plastic. And membranes, things like vapour barriers, you know, the blue paper you see on a timber framed house before the brickwork or whatever goes up. It can be a barrier, a damp proof course barrier underneath a solid floor, or in a leaf of a wall. There's loads of uses you can use of those. And of course there's the obvious bits not mentioned there, so electrical outlets and fittings and fixtures, okay? That's a wall tie. That would be between here, be between the two, cavity here, tying these two together. You get different types of wall tie plastic. What else could there be that's plastic? He just look, as he says, casting his eyes around the room. Oh yes, the vertical blinds maybe. Big sections of the Venetian blinds. Oh dear, the water tanks that you put in for recycling water. It goes on and on and on and on. So you've got to start beginning to think that the plastic's there. It's hitting you in the face, but also it's hidden. Okay, so it's absolutely everywhere, plastic. Do we keep needing to use plastic? We don't know. Glass. I thought I'd touch on glass. I've a bit of coffee here while you look at that. Only coffee's going cold. So this is basically looking at glass in architecture. So we're not just looking at the glass in windows and things. So you can follow this one through. You can use it for facades, so you've got windows, sliding doors, curtain walling as you see on office buildings where it looks like it's all glass. So you've got cladding and facades, that could be structural to a limit. Surface treatments that you put on these, laminated ones, you can print things on them. They can have a chemical coating on them so they shed water and therefore dirt, so they don't need cleaning quite as often. To go construction, not just the facade part construction, you can actually get load-bearing elements out of glass. We've all seen people walking on those glass-floored bridges and balconies, that sort of thing. I've even seen load-bearing beams and portal frames made out of laminated glass. Interesting, but not cost-efficient, really. Here you can use it canopies and skylights for roofs. You can use it for partitions in offices, maybe. Don't forget, you can use glass blocks to build walls with. I've seen glass staircases everywhere. They're quite common, and glass elevators. And you can even get beams and floors. That's a point there. And you've seen it everywhere. Go to a shopping centre, you'll see a lot of glass used in these ways. How's glass manufactured? Well, I'm not doing a history lesson. I've gone straight for the more modern version, which is Pilkington process. If you just type in glass manufacturer into YouTube, you can look at your own video. I didn't include it because they were all a little bit long. And I thought even watching it at 10 times speed might be a little tedious for you. So go and have a look. So it's interesting to watch how they do it. Not dissimilar to the historic way they made lead, which I did show a couple of photos of last time. So, more coffee. What is it now? Time is now 6 minutes past 10 in the morning. It's almost beer time. Sand itself, sorry, not sand, glass itself is basically clean sand, calcium oxide, and a bit of sodium carbonate. And you mix them all up to various proportions. Different proportions produce different glasses, and you can put some extra admixtures in there to make them toughen glass, etc. And that's part of the heat treatment, by the way. It's heated in a furnace. So you heat it up into a molten liquid, and the sand on its own is just raw glass, about 2,300 degrees. Some of you may have seen people making glass things in sort of like those tourist attractions where they're blowing glass and making bowls and stuff. That's interesting. If you put sodium carbonate in, or just called soda, it does bring the temperature down quite a bit. You need to do it. You get this homogeneous blob of molten glass, and they float it on a bed, a big flat bed of molten tin, to form glass of the thickness they want. Molten tin is absolutely flat, so you do get very high quality, very, very smooth glass. Historically, glass was made by spinning a disc of glass. So you blew a bubble on the end of a tube, and then you spun the tube, and a disc grew out from the bottom, and then they'd cut it for the window frames. So if you see old buildings with old glass, you will see curved patterns in the glass. We don't get that anymore, okay? So once it's been floated on the tin, it's then allowed to cool. Now, depending how you cool it, that affects its strength. You can't cool it too quickly. It has to be kept at a certain temperature for a while. It's called annealing. If it's cooled too fast, it gets brittle. So annealing, keeping it at a temperature, is critical to its durability, as it says here. However, making glass uses a hell of a lot of energy and a lot of materials. So a ton of glass requires 4 gigajoules of energy to make. So that's as much energy as a windmill produces in a day, or like 200 homes. So it's quite expensive. On the good side, it is recyclable. Here's just a snapshot of the properties of glass. Well, obviously transparency, we need that. U value, generally a single sheet of glass doesn't have a high U value, but if you put 2 or 3 sheets together with a gap between them, yep, you can get very high U values, and they can be very good insulators. Double, triple glazing. Strength, by nature glass is brittle, but you can laminate them and you can put admixtures in, so you can get toughened glass by annealing, how you do that, or you can get 2 or 3 or 4 sheets of glass and they can be laminated together with a plastic film, so they produce one sheet, so if they do get hit and cracked, they stay together like your car windscreen. Again, YouTube's got loads of videos of idiots trying to smash the stuff. The greenhouse effect, that's really wavelength of visible light coming through your glass and how it's absorbed. Really not a great concern unless you want to put reflective glass in to keep the temperature out, and you can do that by applying an independent film afterwards as well if you want to. Workability, you can work glass, really only when it's hot and malleable, so you can blow it into balls and jars, etc. You can pull it out to make little animal things. You can press it into shapes, so that's how quite a lot of modern bowls, dishes, plates that are glass are made. You can add patterns into it, you can colour it. Recyclable, 100% recyclable. Of course, if you get a bit of laminated glass, then the laminated bit's not recyclable, but you can actually separate that out. And once you recycle old glass, it can be remelted and used again. Rather like old recycled metals can be used again. Solar heat gain, that's the fraction of the solar radiation that enters the building. Basic glass allows most of it to go straight through. You can put reflective films on, you can put a molecule or 2 thick metal film over them. I used to use silver quite often. When you've got double and triple glazed windows, then you may have a coating on the internal sheet of glass where it can't get damaged. Visible transmittance, that's, well, how much you can see through the thing. And that really does vary with the quality of your glass, and do you want it to be completely visible through, or you can give it a sandblasting effect so that you can stand, you know, at your toilet in a pub and no one can see what's going on, but you can still get light coming through. Energy efficiency and acoustic control. Single sheets of glass, no, not good at all. To start getting any efficiency for those, you need to have 2 or 3 sheets, and it's quite normal to do that. Float glass, soda lime glass, clear glass, that's the basic one. Anything from 2 to 20 millimeters thick. Tinted glass is what it says it is on the tin. You can tint it with different things. Toughened glass, which is tempered. It can give you distortions when looking through it sometimes. You used to get it on old cars with toughened glass windscreens. You still use toughened glass in the side windows, by the way. Laminated glass, really good. That's what your windscreens are made of. You can use that for aquariums and staircases and stuff like that. Shatterproof, you put a polyvinyl layer in there, it won't shatter, you don't get sharp edges on it, and you tend to use that again. Things like skylights and windows, especially windows which are within 900 millimetres of ground level to comply with the Building Code of Australia, so that if people stumble and fall against it, they don't hurt themselves. You can get extra clean glass, that's hydrophilic, the water just runs off them, very useful. Double glazed units, won't say anything, we saw a picture of them. Chromatic glass, that's quite a good one. You can get those, there's 3 forms of them. There's the light sensitive ones, the heat sensitive ones, and the light sensitive that are transparent that you can turn on and off with an electric switch. You may have seen these where you've got a clear window or a clear partition wall, and they flick a switch and it's gone. It's got a sort of a foggy white colour. Fantastic they are, I love those. Glass wall, thermal insulation, basically. Glass blocks are solid glass blocks like bricks or blocks, and you can build walls with them or make features out of them. So that's the quick introduction to glass. Next thing to look at, just out of interest, is 3D printing. People don't realise that you can 3D print with most materials nowadays, and the 3D printing of buildings is not a laboratory thing anymore. It's quite widely used in China, and it's used a little bit in America, and it's spreading. So I've got 3 short videos to show you, and here we go. So it's interesting to watch.
The world's first 3D printed community is officially underway thanks to this industrial-sized soft serve machine. I'm just kidding. You do not want to eat that. Meet the Vulcan 2. This 3D printer was made by a company called Icon. It weighs nearly 2 tons and can churn out an entire house in just 24 hours of print time. I wanted to learn more about this machine and what it could mean for the global housing crisis, so I spoke with Icon's co-founder and chief technology officer, Alex LaRue.
What we've been able to do is create something that you just set up once on a foundation. You hook it up to our Magma system. This is our material delivery system that we built in-house, and then you're off to the races. 3 people can operate the Magma and the Vulcan, so 3 people in total for both machines, and then you're printing a house.
We saw the Vulcan 1 earlier this year in Austin, Texas, where it printed the world's first 3D printed home to be awarded a construction permit. The Vulcan 2 features some significant upgrades, including an app for tablet-based controls, more reliable, consistent, and speedy printing, as well as a secret concrete-based mix called LavaCrete.
When you've seen concrete made and mixed, poured into a form, it's doing what it likes to do. It likes to just flow. What we are asking concrete to do is quite different. We're asking concrete to flow a little bit through a hose, but also stand up, right, once we've extruded it. And getting that to happen every single time is a massive technological challenge that we have so far addressed pretty dang well, but I think there's still some room for improvement.
To prove the usefulness of this new technology and bring it to the people who need it the most, Icon partnered with a nonprofit dedicated to fighting global homelessness called New Story. Together, the companies began construction of the world's first 3D printed community in Mexico. So far, 2 houses have already been printed as hot foundations, with finishing by workers from a local nonprofit called Échale.
This Mexico project was about as difficult of a project as you can possibly imagine. It's a seismic zone. It's extremely remote. Power cuts out from time to time. There are safety concerns, in this part of Mexico. It's just not very safe sometimes. You put all that together, and it's just like an enormous challenge, not just from a technology perspective, just operationally.
Icon says they're planning to 3D print a total of 50 houses in Mexico with the Vulcan 2. The community is designed for people living on an average income of less than $3 a day, and residents are set to start moving into their new homes sometime next year. If you're like me, you might be wondering when you will be able to buy yourself a 3D printed home, and how much that might cost. But Icon isn't ready to release all that information quite yet.
The big goal is downloading and printing a home in 24 hours for half the cost, 50%. That's kind of the overarching goal here at Icon. We're not quite there yet, but we're making steady progress towards that goal.
Beyond the obvious terrestrial need for more affordable housing, Icon is also one of a handful of companies currently in talks with NASA about potentially designing 3D printers to build structures on the Moon and Mars. Have you seen any emerging technology you'd like to see featured on What the Future? Let us know down in the comments. As always, thanks so much.
That was interesting, wasn't it? I'm not sure I like the finished surface effect particularly, but it's useful where it was, and because it was in Mexico, a warm country, it didn't need any insulation applied to it. You notice it had natural ventilation up at the ceiling level where the roof was, and all the surfaces were surface fixed. But it's coming. Well, don't think it's just houses, because it isn't just houses. Got to get it to work yet. Why is that one not working? Oh well, I'll have to come back to that one later and find out why it's not working for you. I'll send you the link. One works and one doesn't. And that one doesn't work. Why? Oh, God, I hate this thing. One works and one doesn't. I'll go find them in a minute for you. But 3D printing of entire buildings and warehouses is here. It's not science fiction, and it's developing at a very fast pace. I would think highly likely that as you get into the, maybe 10, 20 years' time in your careers, you'll actually start dealing with 3D printed buildings. So, there we go. Oh, I don't want that. I don't want that. I don't want that. So 3D printing, remember, is real. Okay, it's absolutely real. What's happened here? Oh, I'm struggling today. So then we want to look at sustainability. So there is a unit that you do, BLAR11033, which does a lot about sustainability and environmental impact. So we only really, and you may have done that with me already. Sustainable construction, basically, there's something called the Brundtland Commissions did a report, Our Common Future, and that was back in '87 before things really started to go a little bit wrong. And it was looking at housing and working environments and infrastructure. Okay, they always talk about future generations, so we haven't ruined the planet and used up all the materials for them. So in view of its environment, so we're looking at construction here, so the environmental impact. So sustainable construction involves the design and management of built structures. Okay, doesn't matter what the size they are. The infrastructure could be bridges and things as well. And the performance of materials against all scales throughout. This is the important bit here, their whole use cycle, from construction to demolition, and then hopefully recycle the materials. Try to use renewable energy resources wherever, and I have seen some construction sites online which have got their own wind turbine and solar panels to help them. Doesn't work 100%, they still need some core or base power, but it does reduce what they're using a little bit. There is on YouTube a documentary called Planet of the Humans, which takes the alternate view on all these renewable resources and says that they're not good. You might go and want to look at Planet of the Humans for the alternative view. Economic impact, so suitable construction goes from a linear to a circular economy. A linear economy is you build it and it gets to the end, nothing else happens. Circular is you build it, it goes through its life cycle, when you come back and it doesn't need it anymore, it's recycled and reused. So we're always looking at it. So we're looking at things like water harvesting, generating your own power, trying to be treating your own sewage effluent, etc. There's all these things to do. And then you come down to your social impact. Remember, we're talking construction here. Got to have the highest ethical standards. Isn't it funny to have highest ethical standards in the same breath as construction industry? There are smaller companies that do it. Some of the bigger ones say they do it, but they're always getting caught out, I think. So you need socially viable living, so your design side of it's got to be right. So again, you're looking at connecting people and connecting neighbourhoods together so they're not so reliant on cars and but that all comes from the other unit I mentioned earlier on. The one thing for social impact and economic impact from construction is it does create a lot of jobs, not mentioned here, so you've got to remember all the jobs that you can create. Now, I've only touched on sustainability because I said there's that other unit that you may or may not have done yet. That covers it in a lot more detail. That's really it for now. If I think of anything else, I'll send it out as a small 10-minute recording to you, but I don't think there is. If you go through, look at the unit profile and everything, and if you think I've missed something, please come and tell me, because I'm not infallible, and I'll quickly fill the hole for you. I've now seen one draft of assignment 3. I haven't gone through it yet because I'm still trying to finish off marking for assignment 2. Now I've got this out of the way, that is all I'm going to be doing. This is the last one, as I said, so I do have a little goodbye for you because I've used a Lego background this time because obviously plastic bricks. Ta-ta!
Step 13, enjoy popular music.
Everything is awesome. Oh my gosh, I love this song. Everything is awesome. Everything is cool. Everything is awesome. Always use a turn signal. Park between the lines. Yes. Drop off dry cleaning before noon. Read the headlines. Don't forget to smile. Always root for the local sports team. Go sports team! Always return a compliment. Hey, you look nice. So do you. Drink overpriced coffee.
Here you go. That's $37.
Awesome!
Everything is awesome.
Did you see where are my pants last night?
Everything is awesome.
Plastic!
Instructions coming in from Central. Okay, it says here to take everything weird and blow it up. All right, okay. Let's make it look exactly like it does in the instructions. Hey, buddy, I need a 1x2 keyhole.
No problem, Michael.
2x2 macaroni over here.
2x2 macaroni flying in. Here's one, Mel.
Cheese float! Cheese float! Come on, everybody!
Hey, Roger.
I'm coming at you.
Can I get a couple words over here?
Hey, Gail.
Hey guys, watch me throw this down.
Everything is cool when you're part of my team. Everything is awesome.
Man, it's so good right now! I can sing this song for hours! When you're part of my team!
I know, just a bit of Kevin's stupidity to finish it all off with. Please remember, send back your drafts and I'll answer anything I can. Now I'm just going to find out how to stop the recording. Goodbye everybody.